17b, binomial distributions. Let's read through. There's quite a bit of information here at the start. So it says, now that we have dealt with individual binomial probabilities, we can look at the whole distribution. The binomial distribution is a discrete distribution. In chapter 13 of year 11, when we did this in year 11 course, we devoted that whole topic to discrete distributions. You do remember what discrete means? What does discrete means?
Between two values.
The whole number values. As we have done before, we will draw its graph and we will find the mean and the variance. So notations that we'll be using in here for binomial distribution. The binomial distribution with n independent Bernoulli stages, with each having a probability of p successes, is denoted by b for the binomial. The first number is the number of trials, and then comma p is the probability of success. Okay, so if you see it in that form, that's what those numbers mean. Or alternatively, instead of just b, they could write bin for binomial and comma p. The Bernoulli distribution with probability p is therefore b for binomial, 1 comma p, because the probabilities, because 1 being for one trial, 1 is the total number that you could get there. The x stands for the random variable in the distribution. So to calculate the mean and the variance of a binomial distribution, we have some formulas. Remember, we talked about this last time, that q is equal to 1 minus p, because the probabilities always add up to 1. To find the mean, we use this symbol mu. That should be a flashback from year 11. Mu, or the mean, is equal to the number of trials times by the probability. You might want to put a little arrow in there just to make sure you remind yourself that that is actually the mean. Standard deviation squared, that symbol there, that is called variance. And it is found by multiplying the number of trials times the probability of success times the probability of failure. That's a tongue twister. Don't say that fast. All right. Then to find standard deviation, you square root that. And so this here is standard deviation, SD for standard deviation. In particular, yes?
What is a Bernoulli stage?
A Bernoulli means we have two possible outcomes and one stage, one experiment, probability of success or failure. We're not going to do infinite outcomes, but we are going to do multiple, we could do lots of different stages. Okay, so if we are looking for a particular Bernoulli random variable where the number of trials is 1, obviously that means that the n in all of those formulas that we've just looked at is 1, which means that these formulas here, the n is basically just disappeared because it's equal to 1. It's easy enough, okay? But most of the time you'll use the top row of formulas. Now this doesn't come up terribly often, but talking about the skewness of your distributions, because we are going to be graphing these. Suppose that a binomial distribution consists of n independent Bernoulli trials, each with a probability of p success and probability q, which is 1 minus p for failure. Reversing success and failure reverses the probabilities of p and q and reflects the graph about the point x equals half n. So n being the number of trials, so whatever half of that is the center of your data, and swapping the p and q is just going to reflect that graph across that line, right? Okay, so if p and q are equal to each other, meaning that they'll have to be equal to a half, the distribution is going to be perfectly symmetrical about the point where x is equal to a half. If p is less than a half, then it's going to be skewed to the right. If it is greater than a half, then it's going to be skewed to the left. For distributions with the same number of trials, the standard deviation gets closer to 0 or 1 as the skewness becomes more pronounced. Okay, that's all the theory part. Let's see if we can put it into practice. Here we go. Example number 1. A binomial random variable has parameters n equals 20 and p equals 0.1. Find the mean, variance, and standard deviation. So they are the three formulas that I just gave you. If I want to find the mean, we use mu equals np. That's our formula. N is equal to 20, so it will be 20 times the probability, which is 0.1. Correct, 2. Okay, so we found the mean. Variance is our standard deviation squared, and its formula is NPQ. So it's going to be 20 times 0.1, and Q is going to be 0.9, because it's just 1 minus the 0.1, and that gives 1.8. To find the standard deviation, the complete formula is the square root of NPQ, but rather than calculate that again, since we've already found out what NPQ is, we just want to square root the 1.8. 1.341, something like that. Yeah?
I'll just leave it as square.
Okay.
Wait, can you leave it as a square?
Um,
If we say that approximately.
you don't normally have a decimal underneath a square root sign. That's. Oh, it's a round up, does it? Does it? Oh.
I'm just gonna leave it as.
Oh, you're right. It should be a 2. That should round up to a 2. Okay. All right. That was a nice little one. Moving on. You will have questions where you need to find that, but often there'll be more involved, which there is more. There's more parts here. There's a part B. We're moving on. What is the probability of getting the mean when the experiment is run? So the probability of what was the mean? When we worked it out, 2. So we want to find the probability, and the thing that we want, we call it x. So we want our x to be equal to 2. Now, how do we find that probability? That's what we were doing last lesson. To find the probability, we have 20 trials. If you want to rewrite the information down again, it was n equals 20, p was equal to 0.1, and q we worked out was 0.9. Okay, so yes, correct. 20 trials, so 20C, we want 2 successes, and then we do the 0.1 to the power of 2 and 0.9 to the power of, what will it be? 18. Could you do 20 take away 2, which is 18? And you type that in your calculator.
Good job.
Yeah, there's that. It's written a slightly different way.
Oh, it is written a slightly different way. 1 minus p.
Q is 1 minus P.
Yeah.
So they've just written that in there. So what did we get? Sorry, it was 0.285 in a different form. Like it hasn't got the Q, it just says 1 minus P. But that is Q, so. Part C. What is the probability that the result is within 1 standard deviation of the mean? Now, within 1 standard deviation means 1 standard deviation higher or 1 standard deviation lower on either side of the mean, right? So my mean is mu. I want to subtract a standard deviation off to find how far down that's going to go. Yes. 68 for one either side. Yes, but we're not doing percentages yet. These aren't in percentages. Yes. No, it's a sigma. Yeah, the standard deviation. So for 1 standard deviation lower, our mean was 2 and our standard deviation was 1.34. I'm just going to stop there. 2 decimal places is probably enough. Okay, and that equals 0.66. Then we also want one standard deviation higher. So mu is going to be mu plus the standard deviation, which will be 2 plus the 1.34, and that makes 3.34. Okay, so those two numbers are what we want to find the probability between. Okay, so effectively, we are finding the probability when our result, our score, is between 0.66 and 3.34. Now, no, not negative.
Yeah.
Remember that this is discrete data. What does discrete mean? Whole numbers. We can't have a 0.66 success. It's whole numbers of successes that we can have, right? So I will be finding what's greater than 0.66 is a whole number. The probability of 1 would be my first option. I probably should put x equals 1. Let me rewrite that a bit better. X is equal to 1. Okay, plus the probability that x is equal to 2 and the probability that x is equal to 3. They are the three outcomes that would be between 0.66 and 3.34. Yes, does that make sense? Now we just want to find those three things using our formula. So for each one, first of all, 20 trials, 1 success would be 0.1 to the power of 1 and 0.9 to the power of 19. Then we want to add, let's do the same thing now for 2 successes. Yeah, you could just get it from above.
Is 2 successes?
I've done the 1 already. I'm doing 1, 2, and 3. I'm adding them together. C20, C3 for 3 successes, 0.1 to the power of 3 and 0.9 to the power of 17. What do you get if you type that in?
A large number.
I'll tell you what I got and see if you can get the same thing. 0.745. It's not a large number because it's a probability, so it'll always be between 0 and 1.
With why don't we just do 1, 1, 1 if those different values are like. Why don't we do 1, 2, and 3? Because isn't 2 technically 1 and 2? And 3 is okay.
I want the probability of 1 success, probability of 2 successes, probability of 3 successes. They are 3 separate probabilities I need to add together. Okay. All right, give an example. Oh, don't we like the wordy questions? Give an example that this distribution could model. So we weren't told at the beginning, we were just told that there was 20 things, n was 20, probability of success was 0.1. English marks. Okay, so you need something that has 20 as your total number of things. So I wrote down that you're watching traffic for 20 days. And the probability is 0.1 of success. Okay. Watching traffic. We can make this one work. Watching traffic for 20 days. Okay, recording the number of cars with the last digit of 7, or any number really, because any number, a single digit number, is a 1 in 10 chance, which is why that's my 0.1, my probability of success, right? So last digit of 7 on the number plate.
I don't get this, but that makes sense.
Yeah, you can think of anything, as long as it's got 20 trials and the probability is a 1 in 7 chance for the last digit. 1 in 10, sorry. 1 in 10 chance. Because I
Wouldn't
just
there
did 27.
be values?
No, those are just the number of cars. So, yeah, so this would be, I wanted within one standard deviation of the mean. So there is a 0.745 chance that there will be the cars that I would see would have the last digit as a 7. Because the mean being 2, we worked out the mean, 1 standard deviation either side of that was those scores. Yes, it does make sense? Oh, good. Oh, I thought you were questioning it. Sorry, I thought the question came from you. Oh, good. Does make sense. All right, we'll keep going. We do have quite a bit. We've still got quite a few more questions to do. A binomial random variable has parameters. This time n is equal to 100 and p is equal to 1/5. Find the mean and the standard deviation. Kind of always need those to start with. Yes, Isaac. It will indeed. Very good. Okay, but to find the mean, mu equals, yeah, formula, n times p, and that is 100 times 1/5, which is the 20. Thank you, Ben. Okay, to find the standard deviation, I don't need the variance this time, so I'm going to go straight to the standard deviation formula, which is the square root of npq. So sub in,
20 times 4.
yeah, 100, I just can't do 20. You can put 20 there if you like it. 100 times 1/5 times 4/5, and you square root that to get 4, correct. Keeping p equal to 1/5, what would n need to be increased to so that the standard deviation is less than 1% the number of trials? Okay, we start messing with your head when we... The what is below 1? Correct. So that is, in a formula sense, my standard deviation needs to be less than 1%, but percentages, like we get decimals out of these, right? So we probably need that as a fraction or a decimal, but I'm going to write it as a fraction. If I have n trials, that needs to be n over 100. So my n over 100 needs to be less than, my standard deviation needs to be less than that. Now, yeah, my standard deviation is what, sorry? No. Let me continue with my formula. How can I solve that? Well, yes, the standard deviation formula is square root of npq. So, square root of npq is less than n over 100. Don't want the square root in there, so I'm going to have to square both sides, which is doable. That's okay. So that's going to be npq equals n squared over 10,000. And, or not equals, sorry, that's a less than. Then to get the n squared by itself times the 10,000 over to the other side. So it would be n squared is greater than, so I'm going to have to switch sides here, 10,000 npq. Okay, we do know what the p and the q are, so we can put those in. Let's come over here. N squared. Yeah, I'm gonna get rid of the n's as well. I'm just gonna save that for my last little bit. My 10,000 n times p is 1/5 and q is 4/5. When you times the 10,000 with the 1/5 and the 4/5, you get 1,600 n. Now, I want to know what n has to be. Yes, which is okay because normally it's not okay in an inequality just to divide by something if you don't know whether it's positive or negative.
Oh.
That would be a problem, wouldn't it? Which is why I haven't done it earlier. But n represents the number of trials in an experiment, which can only be positive numbers. So it is okay in this instance to divide through by n and just have that n is greater than the 1600.
And if and could be either or, just like that.
Well, in binomials, n is always going to be positive. But I'm just thinking if we're doing this in another topic and you're doing inequalities, you can't just randomly divide things out if they could potentially be negative numbers. So I'm just putting a note in there that I can do that since n is positive. Okay, so n needs to be greater than 1,600 trials so that the standard deviation is 1% of the number of trials. Okay, let's try another one. C is a similar kind of thing. Keeping that n is equal to 100, p must be decreased so that the standard deviation is less than 1. Okay, that's an actually easier starting line. My standard deviation is less than 1. It wasn't 1%. It wasn't 1% of my number of trials. That was a bit wordier last time. It's just my standard deviation is less than 1. That's a much nicer line. Okay, so we can do, I should read the rest of the question. Can P be increased to give a standard deviation less than 1? Okay, so we're going to do the same kind of setting out. We're going to put our formula in here for the standard deviation. So standard deviation is the square root of NPQ. I'm going to square both sides straight away because squaring 1 is still 1. Okay, so from here to here. No, not square rooting, squaring, which is always positive. So what I'm doing here is I'm just squaring to get rid of the square root signs between there and there. Okay, I want to find the values for P, right? So I don't want Q in my equation. So I can put in that N is 100. I'm going to keep the P and I'm going to change the Q to be the 1 minus P that we know that it is. That way I've just got one variable in there that I need to solve for. Okay, so let's solve this equation. First of all, expand it out. We have 100p minus 100p squared is less than 1. That's a quadratic. So let's put the p squared term, I want it positive. 100p squared, so I'm moving everything to the right. It'll be negative 100p and a plus 1. Because I've switched sides, switch the sign. It'll now be greater than 0. Now, to solve for p, you could try to find two numbers that multiply to give 100 and times to give negative 100, but it's not going to work. We're going to have to use the quadratic formula because it's going to be decimal answers here. So we're going to ignore the inequality sign for a minute and we're just going to use our quadratic formula to tell us the values for p. So p equals quadratic formula minus b would make a positive 100 because the minuses cancel out, plus or minus square root of b squared would be negative 100 squared. Because you're squaring a negative number, you can probably just skip right in the minus sign there, right? Because the minus sign always becomes positive. Then minus 4 times a is 100 times c, which is 1, all over 2 times a, which is 2 times 100. So depends how much of this you want to work out before you go to a decimal. We are going to need a decimal answer eventually. You can simplify that fraction down. Underneath that square root sign, it becomes 9,600 over 200. You can even simplify the third if you want to go there, or should we go straight to the decimal? Straight to the decimal. So you type in 100 plus square root of 9,600 over 200. Which one, sorry, did you get? 0 point? Yeah. Yes. Okay, so they are the two values. I have written the larger one first because that was the first one that I was given. But thinking back to the inequality part of the question, because that's not the solution. This was an inequality, it was a greater than sign in there. That parabola, the one I'm looking at is this one here, okay? The p squared is positive, which means it would be a concave up parabola. And I want to know the parts that are greater than 0. Sorry, what was that? Yeah. Yeah. So what is that though, back in terms of can P be increased or decreased? Yes, it can be both. So it can be decreased to 0.0101 and still be within my standard deviation of 1. Or it could be increased to the 0.9899, and anything in between those would still be 1 standard deviation, less than 1 standard deviation from my mean. Okay, next page, question 3.
Is this a big question? But like, what is a standard deviation?
Standard deviation represents the spread of the scores. So a smaller standard deviation means things are closer together. Larger standard deviation means they're more spread out.
I was just trying to still understand this. I don't understand.
We'll come back to that one, okay? Yeah, we're getting to that. Yeah, or a portion of it. You might not be given the whole. No. You'll be given like a snapshot of the section of the table that will be useful. Which means if you're not getting a value that's in that portion of the table, you've probably got something wrong. Okay, question 3. Two binomial random variables, x and y, both consist of 100 Bernoulli trials for x. P and q are both equal to 1/2, and for y, p is equal to 1/10. Find the ratio of their standard deviations. Ratios. Okay, so I need to find the standard deviation for both of them and write it as a ratio is what that means. So let's do each of them separately. So looking at the x, so for x, what is my standard deviation for the x results? Standard deviation equals NPQ. All right, what is N? 100, yes. What is P? Yes, and what is Q? All right, so my standard deviation equals? Correct. Do the same thing now for Y. So let's find the standard deviation for Y. Square root of NPQ. So there's still 100 trials, but my P and Q are different. P this time is 1/10, which means that Q is 9/10. And what was your answer, Ben? Correct. So the ratio of x to y is going to be 5:3. Ratio of the standard deviations, 5:3. Okay, question 4. I think this is a big one. A few calculations in here. All right. The experiment is to toss 10 coins and count the number of heads. Find the mean and standard deviation and complete the table of probability distribution. So there's a little gap there so that we can work out the mean and the standard deviation first. Oh, you reckon?
Yeah.
Right, okay. No, that's not 0 times, that's the number of successes there. So it's the probability, so that 0 means that I've got 0 heads. I did it. So every single time you're tossing the coin 10 times, the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there is how many heads you get when you do that. And what's the probability of getting 0 heads or 10 heads or 5 heads? All right, wait, slow down. All right, first of all, mean is equal to NP. So our number of coins is 10, and the probability of getting a head or a tail, doesn't actually matter, is a half, which means our mean is 5. Surprise, surprise. That is right in the center of our table. Okay, so then we want our standard deviation, which is the square root of NPQ. So the square root of 10 times a half, which is 1.58. Excellent. Okay, so now we're going to use this, and this is the painful part, because we have to use this table here. We want to find the probability of getting each one of those, but starting with 0. Probability of getting 0 heads. What you're typing in, because you don't have room for working out for all of them, but you have got 10C 0 successes, which would be your, it might be easy to put in 0.5 rather than the half. So 0.5 to the power of 0 and 0.5 to the power of 10. What's easier than that though? That's the formula. It's going to be the power of 10 every time, because all you're moving is 1 from the successes to the failure. So it's just going to be 10C0, 0.5 to the power of 10 every time, and you're just going to be changing that 0 on the bottom to 1, then 2, then 3. All right, so let me bring up my calculator. Oh, I know, I don't use this very often, do I? 10C0 times 0.5 to the power of 10. Okay, so there is the first one, very, very tiny. So I'm just going to do one significant figure. So 0.001. I think I got the right number of zeros there. Yes, because the 9 will round that up. Okay, just change the 0 to a 1. And there's our next one, which is not that much bigger, one decimal place bigger. Because look at my writing over there. All you'd be doing is doing 0.5 to the power of 1 and 0.5 to the power of 9, which is still 0.5 to the power of 10 every time. It will be. Okay, so this is 0.01. Okay, you want to do a few? Make sure you get used to doing these. Do the next one. You do. Where's your calculator?
Stop.
Anyone get the next one? Yep, perfect. Next one. Very good. Oh, okay, all right, yep. All right, so I'm just keeping 2 decimal places for these ones here in the middle. It is symmetrical because once you get to 5, then it's all the same on the way back down again. All right, so does that make sense how to get that table? Everyone's had a bit of a practice with that? Okay, so that is theoretically what should happen. Theoretically. Remember theoretically versus experimentally? Yes. So theoretically, if you were to toss 10 coins, that is the result that you should get. Experimentally, though, it may be slightly different. So part B says, simulate the experiment 100 times. We're not going to do that. I've had some fun looking around a website. You can play with that if you like, to try and simulate the experiment 100 times for 10 dice and how many heads you get. Ooh. Anyway, 10 coins, sorry. Oh, no, the one I was doing, I was looking at one of the ones in the exercise, which was a dice that I was trying to do. Die, you're right.
There's a one-sided die.
It's not dices, it's die. It's the plural. I'm being corrected on my English. Oh, you weren't meaning that? Oh, okay. Anyway. Okay, so anyway, part B is that we are trying to do an experimental probability on this. So the results are already in the table so that we're not having to simulate the experiment. So 100 times the experiment was done and the results are in the table there. It says complete the table of relative frequencies and find the mean and the standard deviation of the data. Okay, so relative frequency. How do you find a relative? That's what the F with the little R on it is, relative frequency. Sorry, what again? Nope, not yet. It's the frequency divided by the total number of things, yes. So to find this one, you'd be doing, how many trials did we do? 100. So whatever the frequency is, to find these numbers in here, you're going to be doing the frequency over 100, right? That's what you're going to be doing to find these. So 0 divided by 100 is still 0. 2 divided by 100 is 0.02. 6 divided by 100 is 0.06. 15 divided by 100 is 0.15. 20 divided by 100 is 0.2. 23 is 0.23. 0.17, 0.13, 0.01, and 0.03, and then back to 0 again. So it's not quite as beautifully symmetrical as the last one was. Now, from this stage, we are trying to find the mean and the standard deviation. We have choices. I thought it might be a good opportunity to revise our year 11 probability and remember how to do the extra columns in the table to find the mean and the standard deviation. So we might do that first as a bit of a recap of year 11 advanced stuff that we did. But then there is a shortcut, which we'll do later. Okay, so the formulas, actually I'll write them down here at the top of the page because I don't have space down there. The formulas that we had from advanced were that variance is equal to the sum of x minus mu squared times the probability of x, or you could use x squared p of x minus the mu squared. Once you've found the variance, the standard deviation is just the square root of that, isn't it? Okay, so we actually had the two different options. I'm going to go with option number 2, the x squared p of x. So to do that, did you write those down? You got those at the top of your page? A recap of our formulas. I'm going to add 2 extra rows to the bottom of this table. The first row is going to be x times the relative frequency. And then because we need the x squared p of x, the relative frequency is my probability, right? Because the relative frequency is the probability that it's occurred. So it's going to be x squared for the second row. We can add those into here. So to find x f of r, you are timesing the x value with the f of r. So again, it's 0 times 0, which is still 0. Then you're going to do the next one. 1 times 0.02 is still 0.02. 2 times 0.06 is 0.12. 3 times 0.15 is 0.45. 4 times 0.2 is 0.8. 5 times 0.23 is 1.15. 6 times the 0.17 is 1.02. 7 times 0.13 is 0.91. And 8 times 0.01, saying a lot of numbers, and 0.27, and back to 0. Okay, so is that all right? We've multiplied those together. Then we need the x squared, which just means you've got to multiply that number by x again. Okay, so you've still got 0 times another 0 is still 0. 0.02 times by 1 is still 0.02. 0.12 times 2 is 0.24. And I'll just write these ones down. 0.135, 3.2, 5.75, 6.12, and 6.37, 0.64, and 2.43, and back down to 0. Okay, now the reason we need the x times f of r, multiplying your score by your probability, hopefully that's ringing some bells, that is how we're going to get our mu, our mean. If you add that top row, so go through and add 0 plus 0.02 plus 0.12, you add all those together to get the total. It was just on a whim. It was truly special. Didn't even think about it. All right, is anyone typing those in? We're still randomly, frantically copying down numbers. So add across the x f of r row. I want to add that row up. You look worried. I got 4.82. Okay, remember the theoretical mean was 5. It's not that far off. Okay, now when we did these in year 11, we called this the expected value of x, but it is the mean. It is the mu. Okay, now the x squared f of r, I need to sum that column, sum across that row, and that one is my variance. So add across that row. Do you want me to tell you? Are you adding? Should wait until Ben does it.
Is the number on top how many times you get it in? Yeah, something like that.
Which number on top? Oh, no, not in a row, but out of the 10 coins. I'm just have 10 coins in my hand.
Yeah.
And I'm just going to drop them on the table, and I'm going to count up how many heads I have. Yes, good. So 26.12. That is the variance. Actually, no, it's not the variance because I was doing this one up here. I'm doing that one. It's the x squared p of x part, but I have to subtract the mu squared to get the variance because I was using that second formula. Okay, so my variance, I haven't got a lot of room here. Variance of x is going to be equal to the 26.12, and then I need to minus the mu squared, which is 4.82 squared. Okay, so that is equal to 2.8876. And then to get the standard deviation, you will square root that to get approximately 1.70. Okay, a whole lot of stuff to do in there. So this was my mu, this is my standard deviation. They were the two numbers that I was actually after. Okay, did all of that as a little recap of year 11 advanced. But we are grateful that there is an easier way. How do you find mean and standard deviation on your calculator from a table of results? You put them in the stats mode in your calculator, correct? I square rooted it because standard deviation is the square root of the variance. Yes. Oh, that's at lunchtime. I'm not kidding. You don't want to see that happen. Yeah. Okay, this is taking a long, let's keep going. We've still got more questions to do. Part C, draw, we now want to graph it. Remember, we want the graphs of these. Draw the theoretical histogram and polygon for part A, and then draw the one from part B, the experimental one. They're little column graphs coming up and then the line going over the top. Yeah, so got to have both of them. So you have to try and fit two little graphs in here. All right, well, as big as you can, but they're not going to be very big in the space you've got.
I'm so dumb.
Okay, so there's my two graphs. On the horizontal axis is going to be the number of heads. So we need from 0 to 10. 0 is not on the axes. You need to move it in so it can have its own column. So I need 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You should make sure that they're all measured, but so 0 has its own little spot. So we're calling this X because X was what was representing the number of heads that we got. On the vertical axis is the probability of getting that number of heads. So that's the probability of X equals X. That was the proper notation. And the probabilities, if we look back, the largest probability in the theoretical table was 0.25. So let's just go up by 0.05s. So they'll have 5 spaces. 1, 2, 3, 4, 5. So it'll be 0.05, 0.1, 0.15, 0.2, 0.25. And then we try to draw lovely little columns. So look at the table up above, the first table. When X was 0, the probability was 0.001. It's really tiny, but technically there is something there. So you've got a pretty much 0 column here. I can't draw anything that small. There we go, little one. Then 1 was 0.01, so that would be a fifth of this space here. So it's going to be about there. Histograms don't have any gaps between the columns, so make sure they're all up next to each other. 2 is 0.4.
Wait, what's 0?
0.01, so it's very, very tiny. This is in the table up above. 3 is 0.12. 4 is 0.21. So you really should be using a ruler for these columns so they're nice and straight. I feel like mine are getting a bit sideways. 5. Oh, really? Oh, dear. It's definitely getting a lean. Oh, dear. Leaning.
Yeah.
Okay, so that's the histogram. The polygon is you put a dot or a cross in the center at the top of each of the columns. And then with a ruler, which I can use a ruler for this, you do a dot to dot. Now also, it should start from 0. So I need to actually join that to the center at the start. And I need it to come back down to 0 as well. So you need an extra space at the end. You've been doing this in advanced?
Possibly.
Debatable. You're watching my ruler. Okay. And I'm just doing a dot to dot here. Oh.
No.
Okay, so I know that's a little bit messy there, but make sure it comes back down to 0. Polygons are meant to start at ground level, do their thing, go back down to ground level again. Okay, now we need to do it again for the next table. So the axes are still the same. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And then 5.
Yep, got by 0.5s, 0.05s. Okay, so here we go again. This time, 0 is definitely 0. 1 is 0.02. 0.06. 0.15.
So the
Uh-oh.
graph that we already drew is
It's the theoretical.
theory.
This is what we did with our this simulated results that we didn't actually simulate because that would have been a pain. There's one in your exercise. You can have fun with that. Oi.
So funny. Definitely not true.
Yes.
Sorry.
Yes.
I'm serious.
Yeah, I'm a bit worried. I can see where this is going too. Oh, yes, that was predictable. I'm pretty sure you want something a bit more challenging than playing basketball with me. That's what you're trying to
insulting.
Oh, that's all right. They can definitely insult my basketball skills.
We know that people. I'm not knowing that.
I know nothing about basketball and I still know that name.
Miss is 0.25.
Oh, sorry. You make sure yours is perfect. All right, we still have more. Quickly draw that down. Actually, sorry, that shouldn't be P of X. This should be our relative frequency this time. That was relative frequency that we're sketching there. All right, are we ready for the next one? No, I said I did.
Oh no, no, I know who LeBron James is. I don't know who Steve Curry is. No. I've heard the name, but I know who Michael Jordan is.
Hey. Oi, okay. Boys, concentrate. Question 5. The experiment is to toss 10 dice this time and count the number of sixes. Find the mean and standard deviation and complete a table of the probability distribution.
Miss, can we do this?
Okay, go for it.
Oh, sick.
Oh no, no, I thought you meant can you do the question?
Oh.
You're not gonna roll. I don't actually have 10.
I
go
have a
hunting.
lot more than
No, you need 10 dice rolled many times. 100 times if we're doing part B, which we're not doing. Okay, so to find the mean, we do the number of trials times the P. So this is just for one roll of the dice. You would expect of the 10 dice that 5 over 3, which is just under 2, you'd expect just under 2 sixes. Expected value versus mean.
after 100
Okay. No. This is just for one roll. One drop of 10 dice. The standard deviation is square root of NPQ, which is square root of 10 times 1/6 times 5/6, which is 1.18 if I round it. Okay, this is calculator practice again. To find the probability from 0 to 10 sixes, you're going to be calculating 10C0 to start with, and it's going to be 1/6 to the power of 0 and 5/6 to the power of 6. And unfortunately, that's not going to be as friendly to type in as the last one because you do actually have it moving for each one. Oh, 10, sorry. Yep, thank you, 10. Yes. Okay, so then you'll do 10C1, just change, don't retype it. If you type it in properly once, you just go back and change the powers each time. Yep, 0.32. 0.29. Does everybody actually know how to do this, or are we just relying on Isaac to give us the answers? All right, I'll tell you the last ones because we've done a very long lesson on this.
You just have no life.
Computer generated.
Oh wow. Miss was non-infinite zero, so we in
It's
one.
very small.
No, it would work. Miss, give me like a solid calculation.
Get it? All right. Simulate the experiment 100 times on a computer. And I'm just going to tell you my simulated results because we're not going to do that. So I had 11, then 28, 31, 21, 9, and then nothing for the rest of them. It's very unlikely when you're rolling sixes to be getting.
I swear said he's wrong.
Sorry? Not in those results, no. You could do your own. No, it's not impossible.
In a roll
But
of 10,
simulation is what I do.
in a roll of 10, I've got these 6 and 5 to 7.
Okay, all right. We're not going to do the long way this time. We're going to do the calculator method. So first of all, f of x. How do I find the f of x? No. Yes, more specific than that. Yes, it's 11. You divide your frequency by the number of trials, which is 100. So 11 divided by 100 is 0.11. That's a little subscript x. All right, who remembers how to do standard deviation on their calculator? Yep, all right, we'll try doing that. Can't get my calculator over. Yes. Oh, I can't actually move it over. So mode 2, 1 for one variable, but we need 2 variables. So we go down and I go 3 for stats and I turn the frequency on. So you're doing the score versus the frequency. So the first 2 rows. So 0. Oh, I have to go back and do it again. You've forgotten. Oh, okay. You press shift mode, down arrow, where it says stat. Oh, okay. I'll go back and do it again. You did it? So you press shift mode, you go down arrow, press 3 for stats, and you go 1 to turn the frequency on. Oh, I think much too much though. All right, I'll start again. Let's start from scratch. Clear all. There we go, clearing everything. So you turn it into stats mode by going Shift 2 and 1 for one variable, and you bring up that table. Then to get the frequency column on, you press Shift mode.
What? I didn't have a shift to do.
Shift button, then the mode button.
Yeah.
Then you press the down arrow so that you can see the one that says stat. Yours might be slightly different because I've given you a different model. Standard deviation. I got 1.13. Did it round? Maybe I didn't round it. That's close. So 1 to turn the frequency column on. Try this calculator because I think that's a different model. No, there was no Shift 2. It was Shift mode. Mode button. So I don't need all those zeros. Down arrow. 4 for you. You got a different model. All right, so did you guys manage to type it all in? You should get that the mean is equal to 1.89 and the standard deviation, actually it might be different because when I did it with the table again. So that might be why I had a slightly different answer. One. You got a different answer? I had 1.13, but did you get 1.14? It's a calculator? Oh, okay, all right. I did it with the table, so that's probably why mine was slightly different, but I'll change it to that. 8. Okay, we've got two different results happening here. Oh, it's a debate. All right, we need some more people to confirm. I had 1.89 with the table. You press Shift 1 to bring up your options. Then I haven't typed all mine in, so mine's not going to work. Then the mean is. Yep. So you got 1.89. And what's the number? Okay, now go Shift 1 again.
It's broken.
4 for variable scan and 3 for deviation. Equals 1.13. Got exactly the same as me. Okay, I'm doing those results because they're the same as mine. All right, so 1.89 and 1.13 as confirmed by Logan. Thank you, Logan. Okay, then we need to draw the graphs. Last thing, draw 2 graphs for each one. One for each one. 1.89 for the mean and 1.13 for the standard deviation.
It's against that working.
Is this to get the results out? You press Shift 1, 4 for variance, 2 is the mean, and 3 is the standard deviation. There's not a lot of graphs in the exercises. We'll do them now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my 0. Okay, so for theoretical, we're doing probability on this axis, and the highest probability, 0.31. Yeah, or 323. So I'm going to go up by 0.05s again. So 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, and 0.35. And the other one is the frequency because it's the experimental one.
Oh.
All right, and then you draw up your histograms. Oh, I should label my axes. This is the X. Okay. So the first table, 0.162. It's hard to be accurate with such little graphs. About there. 1 is 0.323. That's going to be about there. 2 is 0.291. 3 is 0.155. 0.054, that's just above there. 0.013. 0.002. Getting tinier. I'm not sure I can do anything that tiny. So I'm just going to draw a line coming across the board here, a line coming across the bottom here, because it is very, very tiny down there. Okay, then our dot to dot. Don't forget to start at the origin and to the center of each column. Yes, otherwise it's not a proper histogram. And now for the experimental one.
Yeah.
So we're doing the f of x column of the table. So 0.11, 0.28, 0.31, 0.21, 0.09. And then everything else was zeros. Zeros all along here.